Hello, and thank you all for joining us for this webinar session. Today, we will be talking about measuring database performance on bare metal AWS instances. We will cover this topic in two parts. In the first part, I will present our latest Scylla 2.2 versus Cassandra 3.11 benchmark. And in the second part, Glober will talk about the cost of virtualization and why you should consider AWS i3 metal instances. Next slide, please. So before we start, here is a brief introduction of Scylla. Scylla is next generation database architecture that is a drop-in replacement for Cassandra, delivering better tail-end latency and higher throughput, up to 10 times the performance and low tail latency. Our product is open source, and we also have an enterprise edition. Scylla was created by the creators of KVM, the popular hypervisor, and we have our headquarters in Palo Alto, California, and in Israel. Next slide, please. Just a reminder for everyone joining us that the Scylla Summit 2018 is coming up soon at November in the Pullman San Francisco Bay Hotel. Hurry up and register. We will be more than happy to see you there. Moving on, let's introduce our speakers. I am Tomer Sandler, a solution architect at ScyllaDB. I joined Scylla 18 months ago. Prior to Scylla, I worked at Dell EMC, mostly on software-defined storage. With me today is Glober Costa, our VP of Field Engineering. Glober shares his time between engineering department, working on upcoming Scylla features, and helping customers succeed. Next slide. So let's begin by talking about the do's and don'ts of database benchmarking. Benchmarking is no easy task, especially when comparing databases with different engines under the hood. You want your benchmark to be as fair as possible, to run each database on its optimal setup and hardware, and to keep the comparison as apples to apples as possible. Most benchmarks compare different software stacks on the same hardware and try to max out the throughput. However, that is often the wrong approach. A better way is to think about a comparison from the user's perspective. That is, consider the volume, throughput, and latency the database user needs in order to meet his or her business needs. So the goal here is to gauge the resources each database needs to meet established requirements and to see how Scylla 2.2 and Cassandra 3.11 handle these challenges. Next slide, please. So Scylla and its underlying C-star infrastructure fully leverage powerful modern hardware. With Scylla's linear scale-up capabilities, the more cores and RAM, the better. So we chose AWS EC2's strongest instance available, the i3 metal for our Scylla cluster, and created a 4-node cluster. Cassandra, on the other hand, is limited in its ability to scale up due to its reliance on the JVM. The JVM prevents Cassandra from interacting directly with the hardware. Its threads and locks are too heavy and actually slow down as the number of cores grow. And with no NUMA awareness, performance will suffer. As a result, using the i3 metal instance would not yield optimal results for Cassandra. To make a fair comparison with Cassandra, we created a 40-node Cassandra cluster on i3 4x large instances. This recreates a use case we saw for one of our Fortune 50 accounts. And we use a Cassandra Stress as the loader tool for both databases. Next slide, please. Here are the complete details of the setup and configuration we use for Scylla and Cassandra and the loaders in this benchmark. I'll briefly run through it. The instance type and storage. For Scylla, we use the i3 metal, which has 72 virtual CPUs and 512 gigabyte RAM, plus 8 NVMe drives, each of 1900 gigabytes. For Cassandra, we use the i3 4x large that has 16 virtual CPUs and 122 gigabyte RAM with 2 NVMe drives, again, each 1900 gigabytes. Scylla's cluster size was a 4-node cluster on a single DC, and Cassandra's cluster size was a 40-node cluster, again on a single DC. The total CPU and RAM for Scylla was 288 total CPUs, and the RAM size, total RAM size was 2 terabytes. The Cassandra CPU count was 640 CPUs, and the total RAM size was nearly 4.8 terabytes. For the loaders, in the population phase, we used the M42 extra large, and for the latency tests themselves, we used the i3-8 X large, mainly for its 10 gigabit network, so not to be bottlenecked by the network in our benchmark. Next slide, please. So we defined a workload of 38.85 billion partitions, replicated 3 times, 50-50 read-write ratio, and latency of up to 10 milliseconds for the 99th percentile, and throughput requirements of 300,000, 200,000, and 100,000 IOPS. We used our load generator, Cassandra Stress, to populate each database with approximately 11 terabytes, using the default Cassandra Stress schema and a replication factor of 3. Once population and compaction completed, we restarted the Scylla or Cassandra service on all nodes, making sure the actual test started with a cold cache and after all compactions were finished. We tested the latency for various throughputs to have a more comprehensive comparison. We used a wide Gaussian distribution in all the latency tests to achieve as much disk access as possible instead of reading from RAM. Each of the tests ran for 90 minutes to make sure we are in a steady state. Next slide, please. So let's talk about the optimizations we did in each of the databases. It's no secret that Cassandra out-of-the-box performance leaves much to be desired. Cassandra requires quite a bit of tuning to get good results. Based on the recommendation from DataStax and Amy Tobey's guide to Cassandra tuning, we applied the following optimizations to the Cassandra cluster. We used a G1GC garbage collection. We set the heap size to 48 gigabytes. We set the optimizing for SSD to true. And we increased the compaction throughput to 1 gigabyte per second. Originally, we only applied the changes listed here to the Cassandra YAML and the JVM option files. This gave us very poor performance results. Despite multiple attempts using various amounts of Cassandra Stress clients and threads per client, we could not get more than 30,000 operations per second throughput. After applying the IO tuning settings that are listed here, Cassandra started performing much better. Next slide, please. So what are the optimizations we did for Scylla? Well, there's no need to optimize the Scylla configuration. Scylla automatically configures itself to best utilize the setup and will dynamically adjust during the workload. How do we do that? Well, upon installation, the Scylla setup script will test the underlying hardware, mainly the disk, in order to find the maximum useful disk concurrency, as you can see in the graph on the left here. I should mention that Scylla's AMI is already optimized for the AWS i3 instances family. Now, we need to consider what happens during workloads. During workloads, latency increases because once we have more requests than the disk can handle, those requests become queued inside the disk itself. It is then better for the database not to send those requests to the disk in the first place and keep them queued inside the database. Being inside the database, Scylla can then tag those requests and through prioritization, guarantee a quality of service among the various classes of IO requests that the database has to serve. Commit log writes, compactions, read and writes, CQL query reads, etc. Next slide, please. We wanted the latency test to be based primarily on disk access. So we populated each database with a large data set of 11 terabytes consisting of 38.85 billion partitions using the default Cassandra Stress schema, where each partition size is approximately 310 bytes. Each Cassandra node holds a data set that is 5.5 times bigger than its RAM, whereas each Scylla node holds a 16.25 times the data set of the RAM. You can note that the Cassandra 3.x file format consumes less disk space. The November release of Scylla will include full compatibility with Cassandra 3.x format, bringing further improvement to volume and performance. Next slide, please. So now let's talk about the cost of each setup. Scylla's 4-node i3 metal cluster year-term cost is approximately $112,000, whereas Cassandra's 40-node i3 4x large cluster is approximately $278,000. Compared to the 40-node Cassandra cluster, the Scylla cluster provides a 10x reduction in administration workload, 4 nodes against 40. This means all operations such as upgrade, logging, monitoring, and so forth will take a fraction of the effort. As well, it provides a 2.5x reduction in the AWS EC costs themselves. In fact, had we been more strict with Cassandra, we would have had to increase its cluster size to meet the required latency. Next slide, please. So here are the performance results. On the left side, we have the read latency results for 200,000 and 300,000 ops per sec, and the same for writes on the right side. Scylla results are in blue and Cassandra in red. Scylla was able to meet the SLA of 99th percentile latency under 10 milliseconds in all the tested workloads, with the one exception of 12 milliseconds in the read workload under 300,000 ops. Cassandra, on the other hand, was able to meet the SLA only for the 100,000 ops workload. Scylla demonstrated a superior 99.9 percentile latency in all cases, in some cases showing an improvement of up to 45x. Scylla also demonstrated better 99th percentile latency in all cases but one. In the one case where Cassandra was better, right at 100,000 ops, both clusters demonstrated very low single-digit latency. As you can see here, Cassandra demonstrated better 95th percentile latency in most cases. This is indeed an area for improvement for Scylla. You can find the complete comparison charts on our blog post, and you are welcome to visit it. This concludes the first part of the webinar. I will now hand over the lead to Glover Costa, our VP of Field Engineering, to talk about the impacts of virtualization and why you should consider AWS i3 Metal instances.
Thank you, Tomer. As Tomer said, he did a great job explaining the advantages of using a database that can scale up as well as it can scale out, as is the case of Scylla, that allows you to have lower maintenance costs as you have more servers to deal with. But there's another aspect of that is often overlooked. Being able to use larger instances also means that we might be able to use instances that are not virtualized. There are many cloud providers today that offer virtual and non-virtualized offerings, and AWS has recently started doing the same with the i3 Metal offering. If you are talking about using a whole machine, if you're talking about using a bare metal offering, it is essentially impossible these days and uneconomical to use a machine like that that is small in size with not a lot of CPUs, not a lot of memory, not a lot of disks. So if we are using a bare metal instance, we have to use a database like Scylla that is able to use all of the resources to the maximum. And what I'm going to do now is to show the advantages of doing so over using virtualized instances, even for the same family, the same hardware on AWS. The first advantage becomes clear when we just look at the resource distribution in the i3 Metal. What happens here is that for the i3 family, for those of you who are familiar with the AWS offerings, as I move up in the instance scale from 2x to 4x to 8x, what happens is that the amount of resources that I have double, and so does the price. So it's essentially, it doesn't matter if I am using more nodes or less nodes of a larger instances, provided the total amount of requests are the same. The first big advantage of not using a virtualized instance, even before we talk about virtualization itself, becomes clear when we look here at the number of cores and the amount of memory that those offerings have. The i3 16X Large has 32 cores, while the i3 Metal has 36 cores. It becomes obvious that those are the CPUs that the hypervisor would otherwise use and are now made available to the application. the same thing happens to memory. And if we focus on the resource here and the price on the other side, we can see that the price does not change. So for the cloud provider, it doesn't matter if I am using the same instance with a virtualization stack or not. The cost for them is the same, so they're able to charge you the same price. So right from the start, before even talking about virtualization, using the i3 Meadow allow us to have 12% more resources in terms of CPU for the same price. It becomes, if you hit the threshold to use a 16x large to begin with, so if you had a cluster that would otherwise have like 3 or 4 or more of the i3 16x large, using the i3 Meadow becomes a no-brainer because you just have more resources for the same hardware price. The underlying hardware is exactly the same. The storage array is the same. The CPUs are the same. The only difference at this point, aside from the number of CPUs and memory, is that we have a different stack and we have the virtualization stack that is not present on the i3 Meadow. So let's look at the effects of that. To start the evaluation, what I did is that we run a small I/O benchmark. This I/O benchmark ships with the C-star framework that we use for Scylla. And what we are trying to do is try to find what are the maximum bandwidths and IOPS that this storage array can do. And we do this for each of the instances. We see that for sequential 1 megabyte writes, we don't see a difference, nor do we expect one, since the storage array is essentially the same. For 1 megabyte reads, the same situation happens. We have both instances doing around 15 gigabytes a second. All the differences are here in the small digits. And for random 4K kilobyte writes, we also don't see much of a difference. It's nominally higher for 16x large, but that's obviously an artifact of the measurement. When we try to calculate the percentage of that, it's essentially 0. So for most I/O patterns, you're not going to see a difference. But when we come here to the random 4 kilobyte reads, something very interesting happens. Now, this instance is able to do 3 million IOPS. That's what Amazon advertises, and that's the speed for the reads. But the i3 16x large is not able to reach those speeds. And the reason for that we're going to see in details in the next slide. But the i3 16x large simply cannot cope with the rate of interrupts that a workload like this will generate. The i3 Meadow, not having the virtualization engine, we're able to do just fine. If we zoom into what's going on in the CPUs, this is an output of running the perf command that ships into Linux on the i3 16x large on top and the i3 Meadow at the bottom. Now, I don't expect you to understand what this call chain means and what those symbols are. Those are essentially percentage of usage of each function in the CPU. You don't need to know what they do, but if you pay attention, 54% of the time here for the 16x large is spent with Zen something, and then 80% more with FizzDev op hypercall. Those are all things that pertain to the hypervisor Zen that Amazon is using for the i3 family. When we look at the i3 Meadow, all of those symbols are absent because the hypervisor is not there and doesn't have to do anything special when interrupts happen. This is expected to be much better when Amazon starts using the KVM-based Nitro hypervisor instances. The i3 are still using Zen, so Nitro is supposed to be a lot better. But my prediction is that we're always going to see some form of impact from using the virtualization layer. So if the choice is between using the same instance with the same resources with and without virtualization for your database, you're always going to have an edge by using a bare metal instance. While we don't do this, while we're still stuck with Zen on the i3 family, using the i3 Meadow translates into faster I/O for IOPS-based workloads like small reads and things like that. And we see the same logic for networking. Both instances have the same capabilities for network, but what Scylla does is that we're going to isolate, for machines this big, we're going to isolate one of the CPUs just to handle network interrupts, so the CPUs running Scylla don't have to fight for CPU time with interrupt processing. And for 16x large, we're actually isolate two CPUs that belong to the same core, so we're isolating an entire core. If we look at the average utilization in the CPUs that are handling interrupts, the green line is going to show you the i3 16x large. The yellow line is going to show you the i3 Matto. And where you're going to see this is that the i3 Matto interrupt CPUs are not even close to bottlenecking, while the green line, the i3 16x large, both CPUs, this is an average, so both CPUs are very close to bottlenecking. So very soon, we're not going to be able to process more interrupts in these instances, so your workload that deals with a lot of small messages will suffer, and the i3 Matto will be able to keep going just fine. In this slide, we're going to look at the performance of the storage array itself. Forget that we even have a database on top. All I'm looking is that at the latency of the individual requests that are coming from the storage array at the storage layer, regardless of what's going on top. Those are still small requests, and the green line is once again the i3 16x large response time from the storage array, and the yellow line, the average response time for the i3 Matto. So what we see here is not only the i3 Matto has lower latencies, it also has a more well-behaved curve with less spikes, which will translate, of course, at the end at a better performance for the database that is using that storage array to handle its requests. We did test that, so if you look in the next slide, we're doing at a Scylla workload, essentially a random read workload, and all from disk, trying to figure out how long those requests are going to take. If we look at the 99p latency for Scylla running on i3 16x large, we see that the 99p is not that bad. It's actually pretty good for this workload. It's around 10 milliseconds, and it has some spikes here and there to 30, 40, maybe one here close to 50 milliseconds over the course of the benchmark. Now, that's not bad, as I said, but when we look at the i3 Matto, which is the yellow line, it is impressively better. And all we did here was to change the hardware. The 99 percentile latency is below 3 milliseconds for all the duration of this workload. And as you can see, it's way less spiky. And again, all of that is coming from the hardware. The only thing we have changed was the instance type. The full results for this is that if we look at the average latencies, just by using the i3 Matto, I saw a factor of 4. My latencies are now getting better 4 times and are below 1 millisecond in the average. The 95th percentile latency is around 1 millisecond, 5 times better. The 99th percentile latency is below 3 milliseconds, as we saw, around 4 times better. And the 99.9 percentile latency, it's even better in comparison with the 16x large by a factor of 8. I invite you to take a look at the blog in which we published those results, and you're going to see more details about how those tests were conducted and details in general about how those benchmarks were done. Another thing for us to keep in mind is that there are throughput gains to be had as well. I'm not going to have a slide detail this here in the presentation, but what we've did is try to do a write workload, which is equivalent of the population phase of any other benchmark, like Tomer had in his benchmark, and measure how much faster we are for the 16x large, and then in comparison with the i3 Matto. We expect the i3 Matto to be at least 12% faster because it has 12% more CPUs, and the population workload is likely to be CPU bound. But what we see instead is that we are 31%, not 12%, faster than the i3 16x large, and all that extra speed up actually comes from getting rid of the virtualization layer. This is what I have prepared for today. I will remind you once again, as Tomer said in the beginning, that we're having the Scylla Summit in early November in San Francisco. We're going to have 2 days. We're all going to be there. We're hoping to have you there. And the first day before, which is November the 5th, we're going to have a pre-summit training. So if you want to learn more about Scylla, and if you want to have a hands-on session with us, we're going to be there. I'm going to be there. Tomer will be there as well. And we'll be more than happy to have you there. And with that, we'll open for questions. Let me see here in the panel. There are 3 questions already. All right, so I think I have to press answer live for the questions I will answer. So I'll take the first one, Tomer. It says, how do you test your disks to find the best concurrency? So in a nutshell, what happens is that there is a piece of software called Scylla IO Setup. It encapsulates another piece of software that comes from Systar, and it will throw requests at the disk at a certain speed, at a certain concurrency, measure what happens with them, and try to emulate that curve that you saw in the graph. And what we're interested here is in figuring out, like, what is the point over which if I send more requests to the disk, I'm not going to have any benefit in performance. And then I'm not going to, I mean, that's going to be my limit. So Scylla does that automatically. Just when you install it, you run Scylla IO setup, and that would generate a configuration file for you. It's very simple from the user point of view. Okay, Tomer, next one, I guess you can take it. It says, do you have a maximum recommended total data size per node for Scylla?
So it depends on the size of your machines, the total amount of disk space, the type of disk that you're using. Are these NVMEs, regular SSDs, or HDDs, and the RAM size. So we've seen users use 10 terabytes per node and even more than that. It really depends how this data get accessed. Data that get access are either in reads or writes. If the data gets accessed frequently, you will need more CPU power, and the opposite if it gets not so frequently accessed. The rule of thumb is to use a 30-to-1 disk to RAM ratio. For example, for 1 terabyte of storage, you will need 34 gigabytes of RAM. We even have a user who managed to store 60 terabytes, yeah, indeed terabytes, on a medium server, but they didn't access that data that much. And the third question?
All right, so third question that we have here on slide 12. Let me click answer live first. On slide 12, you showed a big difference in the cost between the Cassandra and Scylla cluster. You could have used half the nodes for Cassandra, 20 instead of 40, and therefore reduce the costs and become closer, I guess that's what he wants to know, to the Scylla cost. So why did you do this, and what was the reason behind that? You want to take it? I take it?
Yeah, I'll take it. So if we would have used less nodes for Cassandra, it would not have been able to meet the required SLA for the 99th percentile under 10 milliseconds. As you remember, it was only able to meet the SLA only for the 100,000 ops per second workload. So even with 40 nodes and the optimizations we did in Cassandra, it was not able to meet the SLA beyond the 10,000 ops workload. Also, as mentioned earlier, this was a use case by one of our Fortune 50 accounts. So again, we used the 40 nodes because this is a use case we saw in one of our customers, and because we tried to see that we hope that these 40 nodes will be able to meet the 100,000 and 200,000 and 300,000 ops per second in the SLA that we decided on. But again, it was not the case. And as I mentioned earlier, if we would have been strict, we would have probably needed to go beyond 40 nodes to see exactly how many nodes it took to meet the SLA requirements that we decided on.
All right, there's another question here. How do you measure I/O overhead in virtualized versus metal, since it is expected to bypass the hypervisor? So that's a good question. What happens is that indeed for AWS, the storage, those storage arrays are called local or ephemeral storage. They are not virtualized. They're not going over the network. So the instances are supposed to access them directly. That is indeed much better than in terms of performance if we are using this versus using something else like EBS. But even to drive that I/O, I still need to take interrupts. The operating system running in the guest kernel has to do something, and that's exactly what we measured. My prediction is that when Amazon moves to Nitro, KVM is supposed to be much better with things like this, with I/O, and they're going to have like posted interrupts, and so this is going to be much better for instances that have local storage, that don't have to use any kind of virtualization layer to get to the storage itself. but so far we're still seeing a fair amount of difference in the i3 instances between those NVMEs when they are virtualized versus when the instance is not. And as we saw, the reason is it essentially boils down to interrupt delivery in the operating system. All right. Any more questions? Let's wait a couple of seconds. All right. If you do have further questions, you're always feel free to hit us on Slack, on the mailing list, get in touch. And we also, as we said already, we expect to see you all in the Scylla Summit. Here, thank you very much and see you in the next webinar.
Thank you.